We talk a lot about real time in tech. We throw that term around for, well, pretty much everything
Well,
nowadays.
absolutely. Everything is real time.
Right. Like a tweet shows up on your feed, that's real time. A Slack message pops up on your desktop, real time. But if we're being completely honest, most of that is, let's call it soft real time.
Soft real time is probably a very polite way to put it. I mean,
Yeah.
if your Instagram takes, 3 seconds to register because you're stuck in a subway tunnel, nobody dies, nobody goes bankrupt.
Exactly. It's an annoyance.
Right, it's a UX glitch.
Yeah.
A mild inconvenience at worst.
But today, for this deep dive, we are crossing the line into hard real time, or at least financially critical real time. We're going to be talking about the engineering behind stock trading engines.
The invisible machine.
The invisible machine that decides whether you actually sold that stock at $100 or, $90.
And this is a completely different beast entirely. In the world of high-frequency trading apps, think of your Robinhoods, your E-Trades. Trade Republic latency isn't just a bit of lag. It's a massive liability.
Yeah.
We're talking about a domain where milliseconds literally equal money.
And that is exactly what we are unpacking today. We're doing a deep dive into some really fascinating source material, specifically Chapter 5, Design a Stock Trading App.
It's a great chapter.
It is. But we aren't just going to sit here and look at pretty UI screens and talk about buttons. We are going to completely tear apart the back end, the data pipelines, the protocol decisions, and the absolute nightmare that is rendering complex financial charts on a mobile device.
It really is a masterclass in handling high-frequency data streams. What I love about the source material is that it frames this whole exploration as a system design interview.
Which forces you to actually make the hard choices.
Exactly. It puts you in the hot seat.
Yeah.
If you were tasked with building a trading platform from scratch today, a true greenfield project, how would you actually architect it? What are the trade-offs?
And let's be super clear to everyone listening about the stakes here. If a social media app crashes, people complain on another social media app. But if a trading app crashes during a massive market dip,
Well, the SEC gets involved.
right, you get class action lawsuits.
You lose user trust forever. And in finance, trust is the only product you actually have.
So true.
Hmm.
So let's set the stage here. The source material outlines the scenario where we have a candidate and an interviewer. We are building a brand new stock trading system.
Nice.
What is the actual scale we are looking at? Like, are we building this for a couple of day traders in a basement somewhere?
No, the prompt is very aggressive. They want this system to support 500,000 daily active users, DAU.
500,000 people logging in every day.
Correct. And when you break that down into real engineering terms, that is not just a storage problem. It's a massive concurrency problem.
Because they don't just log in evenly throughout the day.
Exactly. Think about when the market opens. At 9:30 a.m. Eastern Standard Time, you might have 200,000 of those users logging in within the exact same 60-second window.
Wow.
We call that the thundering herd in system design.
The thundering herd. I like that term. It sounds terrifying if you're a server.
It is absolutely terrifying for your infrastructure. You have to design for that peak load, not the average afternoon load. So the requirements laid out are pretty standard but very strict. You need a portfolio view with live prices.
Right.
The ability to buy and sell, so order execution, and historical data for the charts.
And I noticed the source places a very specific constraint here to keep us sane. It says stocks only, no options, no crypto, no futures.
Which is a mercy, honestly.
Yeah.
Oh, absolutely. Derivatives add a layer of complexity to the pricing engine and risk management that would easily take us 10 hours to cover. So sticking to pure equities keeps our focus firmly on the system architecture.
Okay, so we have our functional requirements. It has to buy and sell stocks and show charts. But the non-functional requirements, the how it behaves part, that's where the real engineering actually happens.
Yes.
We mentioned latency as being critical, but the text also highlights smoothness and having a quote-unquote jank-free UI.
Jank is the technical industry term for dropped frames. It's when an app stutters.
And why does that happen?
Well, most modern mobile screens run at 60 hertz or even 120 hertz. That means as an app developer, you have roughly 16 milliseconds to do everything.
Everything, meaning?
Meaning you have to fetch the new network data, calculate any mathematical changes, update the view hierarchy, and actually draw the physical pixels onto the screen, all in 16 milliseconds. If you miss that deadline by even a millisecond, the app drops a frame. It stutters. It janks.
And in a normal app, whatever, but in a trading app, if the price ticker stutters...
The user subconsciously thinks the market itself is stuttering.
Right, it induces panic.
Exactly. A frozen UI implies a frozen market or a crashed order. So performance in this context is actually a psychological feature, not just a technical one.
That is a fascinating way to look at it. Okay, before we get into the heavy plumbing of the network, there is one fundamental trap the source material warns about right out of the gate. It's almost like a hazing ritual for new fintech engineers.
Ah, yes. The floating point trap.
I see this all the time in junior code reviews. Someone needs to store a price, say $10.50. The immediate instinct is to just use a float or a double variable type. It's a decimal number, right? Why is that fatal in a financial system?
It's failed because computers don't think in base 10 like we do. Our human math is base 10. Computers think in base 2, which is binary.
Okay, walk me through why that matters for a dollar amount.
Think about human math. In base 10, you cannot perfectly write down 1 divided by 3.
Right, you get 0.333 repeating forever.
Exactly. You run out of paper before you finish writing it. Binary has the exact same problem, but with different numbers.
Hmm.
You cannot perfectly represent certain very simple decimals in binary, like 0.1.
Wait, 0.1, just one dime?
One single dime. In binary, 0.1 is an infinitely repeating fraction. So if you ask a computer to store 0.1 as a standard float or double, which follows the IE754 standard for floating point arithmetic.
It has to truncate it at some point.
Right, it rounds it off. So it actually stores something like 0.100000149.
Which sounds completely negligible. Like, who cares about the billionth decimal place?
It is negligible if you're calculating the trajectory of a bullet in a video game. But if you're summing up a portfolio of 50,000 shares or calculating compound daily interest, those tiny microscopic errors start to compound. You end up with what we call phantom pennies.
Phantom pennies. And I'm guessing auditors really hate phantom pennies.
Auditors, regulators, your users, everyone hates them. If your app tells a user their portfolio is worth exactly $10,000, but the backend says they have $9,999.99 because of a floating point rounding error, that is a massive, highly illegal bug.
So the source explicitly mandates the solution here. No floats, no doubles, ever.
Correct. The golden rule of fintech is you use arbitrary precision types. If you are coding in Kotlin for an Android app, this is called big decimal. If you're using Swift for iOS, it's called decimal.
But there is a massive trade-off there, isn't there? Big decimal isn't a native primitive type. It's an object. It's heavy.
It is significantly slower. A CPU can multiply 2 standard floats natively in a single hardware clock cycle. It's basically instantaneous.
In big decimal.
Big decimal requires software-level math. It allocates memory on the heap. It triggers garbage collection on the device. It is mathematically heavy. But in finance, correctness always trumps raw speed. You would much rather be a few milliseconds slow and perfectly right than blazing fast and wrong.
Now, I have seen some back-end systems that avoid this by storing money as integers. Like, instead of storing $10.50, they just store the integer on 1,050 cents.
Yes, that is a very valid and common pattern, especially for the database layer. You might store the value as a big int, representing micros or cents. It saves storage space and ensures absolute precision when saving to disk.
But the app still has to display it.
Right. As soon as you bring that integer data into the mobile app to actually do math on it, like calculating a percentage gain for the day, you convert it immediately into a big decimal object.
Got it. Okay, so rule number 1 is respect the math. Now let's talk about the nervous system of this app. Section 2. How did the data actually get from the NASDAQ exchange down to the user's phone? The source proposes a hybrid approach for the API design. Why not just pick one protocol and stick with it?
Because in a trading app, you actually have 2 fundamentally different traffic patterns. It's not a one-size-fits-all situation. You have user actions, and you have market data.
User actions being things like, I want to place a buy order.
Exactly. Or update my profile picture, or show me my transaction history from last month. These are highly transactional events. They follow a classic request-response model. You ask the server a question, the server gives you an answer.
And for this, the source recommends standard HTTP using REST APIs.
Yes. REST is mature. It's universally understood. It has built-in caching headers, standardized status codes. Every developer knows how to debug a REST API.
And critically, as the source points out, it supports things like idempotency, which is a huge concept. Let's unpack idempotency for the listeners.
Imagine you are on a very shaky 4G connection. You hit a button that says, buy 100 shares of Apple, The loading spinner spins and spins, and then your connection drops completely. You have no idea if the server actually received that request before the signal died,
Right. So naturally, as an anxious user, I get my signal back and I hammer that buy button again.
which is human nature. But if the system isn't designed correctly, you might end up buying 200 shares of Apple instead of 100.
Which could ruin someone's day.
Absolutely. So idempotency is a back-end design principle that ensures that even if a client sends the exact same POTA request 5 times in a row, the server only processes and executes at once.
How does it know it's the same request?
REST APIs execute this perfectly using idempotency keys. It's a unique cryptographic ID generated by the phone for that specific button press. The server sees the ID, executes the trade, and remembers the ID. If it sees that ID again 10 seconds later, it just says, I already did this, and ignores it.
That is brilliant. Okay, so HTTP REST handles all the business stuff, the orders, the settings. But what about the actual price ticker? The live feed. I can't keep sending HTTP requests every 10 milliseconds asking, did the price change? Did the price change?
You definitely cannot. That technique is called polling, and it absolutely destroys servers. Think about our scale. If you have 500,000 active users polling your server every single second, that is 500,000 HTTP requests per second just to check a price.
Your AWS cloud bill would be astronomical.
It would bankrupt the startup in a week. So for the live market data, we switched to protocol number 2, WebSockets.
A fire hose.
Exactly, the fire hose. A WebSocket connection actually starts its life as a normal HTTP request, but it includes a very specific header called upgrade:WebSocket.
And if the server accepts that upgrade?
The standard request-response cycle is completely thrown out the window. The server agrees, and a persistent bidirectional TCP pipe is established between the phone and the server.
It's like picking up a phone line and just leaving it off the hook.
That's a great analogy. The line stays open. Once it's open, the phone doesn't have to ask for the price anymore. As soon as the stock ticks on the exchange, the server just shoves that data packet straight down the open pipe to the client. Extremely low latency, virtually zero network overhead.
But WebSockets are notoriously tricky to maintain on mobile devices, aren't they? Mobile connections drop all the time.
They are very fragile. You walk into an elevator, the socket drops. This is where the concept of the heartbeat comes in.
Ping and pong.
Right. The WebSocket protocol has native PNG and PONE frames. The server will send a tiny PNG message every, let's say, 30 seconds. If the client phone doesn't reply with a PNG message within a few seconds, the server assumes the phone drove into a tunnel, and it cleanly cuts the connection to save resources.
And I assume the client does the same thing.
Yes, it's mutual. If the app doesn't hear a POG from the server, it assumes the line is dead and attempts to silently reconnect in the background. This entire heartbeat dance prevents zombie connections.
What's a zombie connection?
That's when your phone's operating system thinks the socket is still open, so the app shows you a stock price of $150. But the connection actually died on the server side 10 minutes ago, and the real price is $140.
You are just staring at a ghost.
And you might try to make a financial decision based on that ghost. In a trading app, displaying stale data is instantly worse than displaying no data at all.
So the source material essentially validates this hybrid stack. REST for the structured, transactional orders, and WebSockets for the streaming market data.
Yes, and it notes that industry giants like eToro and Trade Republic use this exact same hybrid architecture. It's the battle-tested standard for a reason.
I noticed in the REST API section, the source mentions pagination for fetching the user's order history, and it explicitly suggests using offset pagination. Now, usually in system design, I hear engineers bashing offset pagination and saying you should always use cursor-based pagination. Why stick with the simpler offset model here?
That's a great catch. It really comes down to the fundamental nature of the data you are serving. Cursor pagination, where the API uses a pointer to the last specific item you saw, is fantastic for infinite feeds. Think of Twitter or TikTok, where thousands of new items are constantly being inserted at the very top of the feed while you're scrolling.
Right, offset pagination breaks there because if new stuff is added, all the page numbers shift down and you see duplicate posts.
Exactly. But think about an order history in a brokerage app.
My past stock purchases don't change.
Right. Order history is an immutable append-only ledger. Old orders are never deleted, and new orders only ever get added to the very end of the list. And crucially, users behave differently here. In a social feed, you just mindlessly scroll down. In an order history, a user might want to specifically jump to page 5 to see what they bought during a market dip last year.
Oh, and offset pagination allows you to jump to a specific page number easily, whereas cursors force you to read sequentially.
Exactly. Offset is incredibly simple to implement on the back end, and it perfectly matches the user behavior for this specific feature. It's a great example of not over-engineering a solution just because a different tool is trendy.
Fit the tool to the requirement. I love that. Let's move on to section 3, the fortress. We have this massive system, we have to secure it. The source introduces the concept of the API gateway. I usually describe this component as the bouncer of the nightclub.
That is the perfect analogy for it. The API gateway sits at the very absolute edge of your back-end infrastructure. It is the single, unified entry point for all mobile traffic.
Why do we even need it? Why can't the mobile app just talk directly to the order service or the user profile database?
It comes down to security and sanity. First is authentication. When the phone sends a request, the API gateway intercepts it and checks your your JSON web token. It verifies your digital signature. If you aren't who you say you are, or your session expired, the gateway rejects you right at the front door.
So the internal microservices never even know you tried to get in.
Exactly. It saves massive amounts of processing power for the internal network. The internal services can just blindly trust that any traffic they receive has already been fully vetted and authenticated.
Second reason.
Rate limiting. Remember that thundering herd of 500,000 users we talked about? Or worse, a malicious botnet trying to DDoS your servers to crash a specific stock.
The gateway stops them.
It implements routing algorithms like the token bucket or the leaky bucket. It looks at the incoming IP address and says, okay, user A, your plan allows you to make 10 requests per second. You just sent your 11th request. Request denied. It returns an HTTP 429 status code. Too many requests.
So it acts as a physical shield, protecting the internal infrastructure from being completely overwhelmed.
A shield and a
Yeah.
traffic cop. Because the third job is routing. The mobile app doesn't need to know the IP address of 20 different microservices. It just sends everything to one URL, like ap.stockapp.com.
And the gateway looks at the URL path.
Right. It says, oh, this request is for /orders. I'll forward that to the order service cluster. This one is for /market data. I'll route that to the WebSocket cluster. This completely decouples the client application from the back-end topology. You can rewrite your entire back-end architecture, and the mobile app won't even notice.
That is incredibly powerful. Let's shift gears and jump to the client side. The actual code running on the user's iPhone or Android device. The source strongly advocates for using clean architecture. Now that is a massive buzzword bingo winner on tech blogs, but what does it actually practically mean in this context?
Clean architecture is fundamentally about the strict separation of concerns. It visualizes the application code as concentric layers of an onion.
Okay, peel the onion for me.
At the very center core of the onion, you have your entities. This is your pure business logic. The rule that says a stock object must have a symbol string and a price decimal. That core doesn't know anything about Android or iOS.
It's just pure logic.
Right. Around that core, you have your use cases.
Yeah.
The specific actions the app can perform. Place order, fetch portfolio. And then on the outermost layer, you have your interface adapters. This is your UI framework, your buttons, your screen, and your database connectors.
And the golden rule of this onion is that the inner layers should never, ever know anything about the outer layers.
Exactly. Your core buy stock logic should never know that it's being triggered by a specific green rounded button on an iPhone screen. It shouldn't care if the price data is coming from a REST API over 5G or being loaded from a local SQLite database on the phone. It just processes the rules.
Which brings us nicely to the repository pattern that the text heavily emphasizes. I always like to think of the repository as the head chef in a restaurant.
I like that. Walk me through it.
So the UI, the screen the user's looking at is the waiter. The waiter comes back to the kitchen and says, I need the user's portfolio data for table 4. The waiter doesn't care how the meal is made. They don't care if the chef cooks it fresh by fetching it from the network API, or if the chef just grabs it from the warming rack because it was cached in the local database 10 minutes ago. The waiter just wants the portfolio data to serve to the customer.
That is a phenomenal description. The repository is the ultimate arbiter of data. It encapsulates all the complex decision logic. It says, is the network available right now? Yes. Okay, let me fetch the fresh data from the remote API, save a copy of it to the local phone database, and then pass it up to the UI.
Or if the phone is in airplane mode?
The repository catches the network error, realizes it has no signal, and says, okay, I will just query the local database and give the UI the cached portfolio data we saved yesterday.
So it guarantees the UI always gets something.
Yes. This is crucial for the single source of truth principle. In modern mobile architecture, the local database on the phone is the ultimate truth. The remote network is just a mechanism used to update that local truth. And the UI simply observes the truth and draws it.
Speaking of updating the truth, we need to talk about caching. The source makes a really aggressive black and white distinction here. It says you must absolutely never cache real-time stock prices to the device's physical disk.
And that is a non-negotiable rule. Think about the physical hardware constraints. The input-output cost of writing data to the flash storage drive on a phone is incredibly slow. We are talking tens of milliseconds slow.
Which in our context is an absolute eternity.
Exactly. If the price of Tesla is updating 50 times a second over your WebSocket and your app attempts to open a database transaction and write every single one of those ticks to the hard drive,
The app would just lock up.
you will completely block the main thread, the app will freeze, and you will physically burn out the user's battery in an hour. And for what? By the time the disk finishes writing that specific price, it's already stale. The market has moved on.
It's like trying to take a photograph of a speeding bullet, printing it out and framing it on the wall every single millisecond. It's totally pointless.
Pointless and destructive. So for real-time streaming data, we strictly use in-memory caching only. We store the latest price in a simple variable in the RAM. If the user force kills the app, that variable is wiped out. It's gone.
And that's fine, because if the app is dead, the user isn't looking at the price anyway.
Exactly. When they reopen the app, we just fetch the new current price. Now, for historical chart data, the strategy is completely reversed.
Right, because historical data is static.
Exactly. The closing price of Tesla on January 1st, 2022 is a historical fact. It is never, ever going to change. So you absolutely cache that heavy data payload to the local disk. That way, the next time the user opens the 5-year view on their chart, it loads instantly from their local storage. You completely bypass the network.
Okay, this is the perfect segue to the visual heavy hitter of this deep dive. Section 4, the battle of the charts.
This is where so many trading apps go to die. Rendering a dense financial chart is, without question, the single most computationally expensive task the UI thread has to perform.
Really? More than video or animations. I mean, to a user, it just looks like some green and red rectangles and a few squiggly lines.
It looks simple, but let's look at the sheer data density involved. A standard single trading day has 390 open market minutes. That means you are rendering 390 individual candlesticks. And each single candlestick consists of an open price, a high price, a low price, and a close price, OHLC, plus the trading volume bar at the bottom.
So that's essentially 5 data points per minute times 390 minutes. That's almost 2,000 data points just for one day.
Now imagine the user switches to the 1-year view, or adds 3 different moving average indicator lines over the top of it. You are suddenly asking the phone to process tens of thousands of floating point math operations.
And it has to map those numbers to physical screen pixels.
Exactly. You have to run an algorithm that dynamically maps a price of $150.50 to exact y-coordinate 400 on the screen, and the timestamp 10:30 a.m. to exact x-coordinate 200. And you have to recalculate that entire matrix of pixels 60 times a second while the user is actively pinching and zooming their fingers on the glass.
That sounds like a complete nightmare to program.
It is. The source outlines 4 different approaches the industry uses to solve this. Let's walk through the contenders. Option 1 is using pure native graphics. We're talking about using the raw canvas API on Android and core graphics on iOS.
This sounds like the hardcore developer mode. You are basically drawing every single pixel manually using math.
It is.
It is blazing fast. You are as close to the metal GPU as you can get.
You have to write all the complex rendering code twice. The mathematical logic for drawing a candlestick and handling a pinch-to-zoom gesture in Kotlin for Android is completely different from the Swift code required for iOS.
It sounds like a maintenance nightmare for the engineering team.
It's awful. If your designer wants to change the border radius of a candle, 2 different teams have to go rewrite complex geometry code.
Okay, option 2. Third-party native libraries. Things like MP Android Chart or iOS charts.
This is the practical, everyday choice for most standard apps. Someone else already suffered through writing all the hard math. You just plug in the library and feed an array of data.
But there's a catch.
The catch is that deep customization is your enemy here. If your design team wants a very specific animated gradient fill under the line chart that the library author didn't anticipate, you are stuck. You end up spending weeks trying to hack and fight the library to make it do something it wasn't designed for.
Option 3 mentioned is server-side rendering. Basically, the backend server uses a powerful graphics card to draw the chart, saves it as an image file, and just sends a JPEG or PNG to the phone.
We can dismiss this entirely for a modern premium trading app. It feels completely dead to the user. You can't tap on a specific candle to see the price. You can't fluidly zoom in. It's like looking at a static photograph of a chart. Users hate it.
Which leaves us with the controversial winner chosen by the source material. Option 4, WebView-based rendering.
Oh, I can literally hear the native iOS and Android developers groaning right now. Web views in a high-performance critical financial app.
It does feel like a bit of a betrayal, honestly. We just spent 20 minutes stressing about the absolute importance of native big decimal precision and native multi-threading concurrency, and now we're just going to drop a heavy web browser right into the middle of the screen.
It sounds counterintuitive, but there are two massive reasons why this is the industry standard. First is absolute visual consistency. Financial charts require extreme precision. You want the Fibonacci retracement indicators and the logarithmic scales to look 100% visually identical on the Android app, the iOS app, and the desktop web platform. Sharing a single web-based rendering engine guarantees that consistency.
And the second reason?
The ecosystem. The open-source JavaScript libraries available for financial charting tools like TradingView or D3.js are light years ahead of anything available natively. They've had thousands of developers optimizing their rendering pipelines for over a decade.
So we are essentially swallowing our native pride to leverage the billions of dollars of investment that has gone into making web browsers incredibly fast at rendering graphics.
Correct. But, and this is a monumentally huge, but integration is not free. You cannot just load a URL into a web view and hope for the best. That is exactly how you end up with a laggy, terrible one-star app. You have to build a highly optimized communication bridge.
Which brings us to Section 5, optimizing the bridge. This is the real technical crux of the entire architecture. We have our native code say Kotlin receiving high-speed raw data from the WebSocket, and we have a web view running JavaScript waiting to paint that data onto the screen. They speak completely different languages and run in different memory spaces.
Right, so we need to constantly pass data across that boundary. In Android, you use an interface called @JavaScript interface. In iOS, you use WK-script message handler. The API exists, but here is the massive bottleneck. Serialization.
Explain serialization for us.
You can't just hand a Kotlin memory object over to JavaScript. You have to convert that complex object into a standardized string format, usually JSON. We call this stringifying the data.
And stringifying is slow.
It is extremely CPU intensive. If you try to stringify a massive array containing 10,000 historical data points and shove that massive 1 megabyte string across the bridge, while the user is actively scrolling the chart,
The CPU maxes out.
the app will completely freeze for half a second while it processes the string.
So how do we fix it? How do we make the bridge fast? The source lists 3 major optimizations here. First up, buffered updates.
This goes right back to our WebSocket firehose problem.
Yeah.
If the socket receives 50 price updates every single second, and you try to serialize and push 50 individual updates a second across the JS bridge, you are flooding the bridge with traffic.
You are constantly interrupting the web view.
Exactly. You are forcing the JavaScript engine to halt, parse the JSON string, and trigger a full re-render of the HTML canvas 50 times a second. It's completely wasteful. The human eye cannot even track a number changing that fast anyway.
So we use a buffer.
Right. We collect the incoming ticks in a simple native Kotlin list in memory. We just hold them. Then, on a background timer, say every 500 milliseconds, we bundle all of them up and send one single batch update to the web view.
So instead of 50 small interruptions, you do one medium one.
Exactly. The native side says, hey, JavaScript, here's an array of the 25 price changes that happened in the last half second. The JavaScript parses that array once, updates its internal state once, and executes one single paint operation to the screen. It results in a dramatically smoother chart and uses far less battery.
That makes perfect sense.
Mm-hmm.
Optimization number 2, offloading logic.
This is critical. JavaScript running inside a mobile web view is strictly single-threaded. If that single JS thread is busy doing complex math, like calculating a 200-day exponential moving average or parsing complex time zone strings into formats like Friday, Feb 21st, it isn't drawing pixels, it blocks the UI.
So we force the native code to do all the homework first.
Yes. Kotlin and Swift have amazing, simple multi-threading capabilities. We spin up a background worker thread natively. We do all the heavy math. We pre-format all the text strings. We construct a highly simplified, totally flat view object that requires zero calculation. And we hand that pre-chewed object across the bridge.
You turn the JavaScript into a dumb painter.
Exactly. The JS receives the object and basically just says, okay, I will paint this exact string at this exact coordinate. No thinking aloud.
Love that. And optimization number 3, smart loading or level of detail rendering.
This technique is mostly used for the heavy historical data. Let's say I want to load a 5-year chart. The physical screen on a mobile phone only has roughly 1,000 pixels of horizontal width. You physically cannot display 5 years of minute-by-minute data on that screen. That'd be millions of data points overlapping on a single pixel.
It would just look like a solid block of ink.
Right. So the optimization is simple. Don't download them. When the chart is zoomed all the way out to the 5-year view, the native code asks the REST API for weekly candlestick data.
So it's a very tiny payload, very fast to download and bridge.
Exactly. Then, as the user places their fingers on the screen and starts zooming in on a specific month, the web view fires an event back across the bridge to native. It says, hey, the user is zooming in on March 2023. The native code dynamically fires a new API request to fetch the daily candles for March, then the hourly candles, and finally the minute candles as they zoom closer.
It's exactly how Google Maps or Google Earth works. When you are looking at the whole globe, it doesn't try to download the high-resolution street view textures of Paris. It only downloads the street data when you actually zoom your camera down into Paris.
That is the perfect analogy. It keeps the memory footprint of the app incredibly low and guarantees the initial chart load is snappy.
Let's move into the final major section of the architecture, resilience and scalability. We have spent all this time building an incredibly fast, highly optimized sports car. Now we need to figure out how to drive it on a terrible, bumpy dirt road.
The bumpy dirt road being the global cellular network. Mobile networks are deeply hostile environments for software. Users walk into elevators, they take the subway, their phone hands off from a 5G tower to a terrible public Wi-Fi network.
How does the trading app handle that tunnel scenario when the signal just drops dead?
This touches on the ethics of the UI, what I like to call the lie of the UI. If the WebSocket suddenly disconnects, the absolute worst, most dangerous thing your app can do is just leave the last known price sitting on the screen without any visual warning.
Because I might look at it and try to execute a trade based on a price from 5 minutes ago.
Exactly. The UI must be brutally honest with the user. The moment the heartbeat ping fails, the app needs to instantly switch to a connecting state. It should gray out the chart or overlay a massive data is stale warning banner.
And what happens when the train finally comes out of the tunnel and we get 5G back?
We obviously need to reconnect the WebSocket, but we have to be extremely careful how we do it. If a commuter train carrying 100,000 users comes out of a subway tunnel at the exact same moment,
and all 100,000 phones instantly ping the server to reconnect,
you just accidentally launched a massive DDoS attack against your own infrastructure. You will crash your own servers.
So how do we prevent the phones from overwhelming the system?
We implement an algorithm called exponential backoff.
Walk me through how that works.
When the signal returns, the phone tries to connect. If the server is busy and rejects it, the phone doesn't just immediately hammer it again. It waits exactly 1 second and tries again. If it fails, it waits 2 seconds, then 4 seconds, then 8 seconds.
It exponentially increases the delay between attempts.
Exactly. And crucially, we add a mathematical variable called jitter. We add a random number of milliseconds to each phone's delay. So phone A might wait 4.2 seconds and phone B waits 4.7 seconds. This completely smooths out the traffic spike and gives the back-end servers breathing room to actually recover and process the backlog.
That is incredibly smart. What about the battery impact? Keeping a cellular radio constantly active to listen to a WebSocket stream has to be a massive battery drain.
It drains power extremely fast. This is why the source emphasizes a strict mobile lifecycle rule, background disconnect.
Meaning, if I hit the home button to check a text message, the app pauses.
It must immediately sever the WebSocket connection. There is absolutely no point in streaming thousands of live price updates to a chart that the user cannot physically see because the app is minimized. So the moment the operating system calls the on-pause lifecycle event, you gracefully kill the socket. The moment the user swipes back to the app and triggers on resume, you wake up and reconnect.
But wait, isn't there a delay then? When I reopen the app, the socket takes a second to connect. Do I just stare at a blank screen?
There is a slight delay. But that is exactly where our hybrid REST architecture comes back to save the day. The instant you open the app, the native code fires off a fast HTTP REST request that says, give me a snapshot of the current state.
Because standard HTTP requests are very fast to establish.
Right. It grabs the current prices and immediately paints the screen so the user sees data. Then, quietly in the background, it negotiates the WebSocket upgrade to handle all the subsequent real-time ticks.
Ah, so the REST API provides the initial state, and the WebSocket handles the changes to that state.
That is the absolute gold standard pattern for this problem.
We have one final technical challenge to cover, back-end scalability. We have 500,000 concurrent users. Do all of those users actually need to receive the price update for every single stock on the market?
God, no. That brings us right back to the fire hose problem. If the server tried to broadcast every single millisecond tick for the entire S&P 500 to 500,000 phones, the bandwidth costs alone would be millions of dollars a month. And the mobile processors would melt trying to discard the data they don't care about.
So we need some kind of subscription model.
Exactly. We implement a pub/sub, or publish-subscribe system, on the back end, typically backed by high-throughput messaging brokers like Redis or Apache Kafka. When the mobile client establishes the WebSocket, it sends a specific payload. Subscribe to Apple, Google, and Tesla.
Basically saying, I only care about the stocks currently visible on my screen.
Right. The server registers that specific WebSocket connection ID against those three specific stock ticker topics. When a price tick comes in from the NASDAQ queue for Apple, the server quickly queries the database. Which specific socket IDs are subscribed to Apple right now? And it pushes the data packet strictly to those specific users. It filters out 99% of the noise at the source.
That significantly reduces the network payload.
It's the only mathematically possible way to scale a system like this. You have to filter at the source.
We have covered a truly massive amount of ground today. Using big decimal objects to guarantee mathematical precision, building a hybrid REST and WebSocket nervous system, applying clean architecture to separate our logic, navigating the intense battle of WebView chart rendering, and implementing resilient patterns like exponential backoff to keep the whole thing from crashing.
It really highlights the fact that building a modern trading app is not just about slapping a pretty UI on top of an API. It is a deep system engineering challenge. Every single layer of the stack, from the database column type all the way up to the pixel rendering pipeline, is tightly coupled to the incredibly unforgiving constraints of the financial domain.
Before we wrap up, I want to touch on the final what's next section of the source material. It briefly alludes to the concept of offline functionality, and I really want to get your expert take on this. In a standard app, like a Notes app or an email client, offline support is amazing UX. You write an email while on an airplane, and the app just queues it up and quietly syncs it when you land. Should a stock trading app allow offline orders?
Oh, that is the most dangerous question in fintech design.
I mean, on paper, it sounds like great user experience. A button that says, queue order for later.
It is a fundamentally terrible idea for a trading platform.
Really? Why?
Because of a concept called slippage. Let's go back to our tunnel scenario. You are sitting on the train, you lose your signal, you open the app, and you see a cached historical price for a stock at exactly $100. You think, great price, I'm going to buy. You hit a button that keys a market buy order.
Okay.
You sit on the train for 10 minutes, you finally pull into the station, your phone reconnects to 5G, and the app automatically syncs and executes your queued order in the background.
But the actual market price of the stock is now $110.
Exactly. Or $120. You just paid 20% more than you intended to because of the time lag. Or, even worse, what if bad news broke while you're in the tunnel, the stock crashed to $50, and your app automatically bought you into a falling knife?
Oh, wow. Yeah, that would be devastating.
It's a massive financial liability. So in this specific, highly volatile domain, the engineering philosophy of fail fast is vastly superior to queue later.
So friction is better than seamlessness here.
100%.
Yeah.
It is infinitely better to just pop an error message telling the user, unable to trade, no internet connection, rather than quietly executing a financial contract based on 10-minute-old cached information. Sometimes, good UX is actually preventing the user from doing what they think they want to do.
That is a profoundly interesting thought to end on. Friction as a safety feature.
In fintech, the engineering itself is the product. Trust is built entirely inside those constraints and rules.
So the next time you open your portfolio, tap the buy button, and that little green confirmation check mark magically appears instantly on your screen. Just take a second to remember the massive invisible machine, the arbitrary precision of the big decimal, the persistent heartbeat of the WebSocket handshake, the heavily buffered JavaScript bridge drawing your chart, and the exponential backoff algorithms that made it all happen without your phone melting in your hands.
It really is a miracle of modern distributed engineering.
Thanks for diving so deep into the architecture with us today. This was fascinating.
Always a pleasure to break these systems down. Keep learning, everyone.